Thank you. Thanks for attending my talk. Today I'm going to be talking about some of the lower hardware level causes for performance swings due to code placement and alignment. Everyone's favorite topic. So my agenda looks kind of like this. I'm going to spend a couple of slides to discuss, well, what is the purpose of this presentation? Then I'm going to give a quick intro into the workings of the Intel architecture front end, which will serve as a prerequisite for some to better understand some of the examples I'm going to show, which is going to be the main part of this presentation. And then I'll wrap it up with just a couple of final thoughts, comments, what to do, future work. So what is the purpose of this presentation? Well, as the title suggests, it is an introduction into some of the more subtle, low-level architecture-related causes for performance swings that aren't immediately obvious by just looking at the higher-level source code or assembly code or disassembly code. So why is this important? Well, I think this is important for various reasons. And for example, one of them is as a means to determine whether you have a change set that's good or not, or to be able to better identify that. So I'm just going to go through just some real quick examples. Let's say you have an optimization that you're working on, and you've identified it by looking at a benchmark. So you write this optimization, you implement it, you do some testing locally on it to make sure it works, it's firing, it looks good, then you're kind of excited to fire off the whole benchmark or benchmark suite, only to be disappointed that you really didn't get the improvements that you're hoping for, or maybe even worse, it regressed the benchmark. So does that mean that your optimization is bad or your expectations were wrong? Well, maybe, but it could be that your expectations and optimization are fine, and upon closer inspection, you see that the piece of code that you're targeting actually does speed up. But code kind of shifted a little bit, or something happened, and either that same piece of code or somewhere else you're affecting alignment or some other hardware effect that's more subtle that's causing a regression and effectively either masking your improvements or causing a net regression. Another example, this one I think is more common. I'm guessing at least some of you have run into this. You make some changes and you're not all excited to run performance testing on it because there's no reason to. You're pretty certain that your changes aren't going to affect performance. So you do stability testing, check it in, but next morning you wake up, you have an email, hey, you regressed this benchmark. You're like, what? So you're confused, you grab the benchmark, you do a before-after diff with your changes, and you stare at the code, and you're like, this still makes no sense. There's absolutely no reason these changes should affect performance in the least bit, up or down. Super annoying. The last example I have here is I titled as Help When Performance Results Lie to You. So let's say you have an optimization idea, and for the sake of this example, let's say a new instruction sequence. A common way of evaluating something like this is to stick it in a micro benchmark, right? So you take a baseline where you have the existing instruction sequence, you put it in a tight loop, then you take your experimental instruction sequence, stick it in a tight loop, just run them both, time it, and whoever wins is the better instruction sequence, right? That's kind of reasonable for some cases. So let's say your case wins, and clearly your instruction sequence is better and you check it in. Well, what if it's not? What if it's actually worse? And the only reason your micro benchmark ran faster was because something, again, lower level, subtle architectural effect was causing the baseline run to run much slower than it has the potential to, causing you to make the wrong decision. So these are just some examples real quick. Maybe some of you can relate to some of these, but there are lots more examples. And in my personal experience, I've seen this kind of issue pop up quite a bit. It becomes pretty frequent. And they're hard to identify. But I think that if you do care about performance, I think it's important to at least learn about some of these and be able to identify them better. And in order to be able to do that, I think it's important to have a better understanding of the architecture and to at least be exposed to some examples that show how weird performance swings can happen. And that's kind of what I'd like to do with this presentation, is to kind of expose some of you to some of the basics of the architecture and to show some examples of, okay, well, how does code layout affect performance? Just a quick note before I go on, and that's even though we can learn to identify some of these cases, they're not always simple to resolve. Some of them are just too low level for the software to be able to either detect or come up with reasonable heuristics to be able to fix them. Okay, so enough of that. Let's get into the fun stuff. So Intel Architecture Front-End 101. So just a couple of quick slides before we get into my examples to explain how the front end of the architecture works for those that aren't quite familiar with it. To do this, I'm going to compare two different generations of Intel architecture. The older gen, which includes the cores and the halems and the atoms, including some of the current atoms. So really overly simplified diagram of the front end. Basically what happens is you grab 16 bytes of instructions in a 16 byte aligned window. You take these bytes and you feed them into the decoder. The decoder decodes these instructions into smaller micro ops or UOPs and feeds those into the rest of the pipeline to eventually be executed. After that first 16 bytes is fetched, in the next clock, we fetch the next 16 byte chunk of instructions, aligned window. It could be the next contiguous one or somewhere else based on how the branch predictor steered us. We fetch those, decode those, and so on and so forth. We keep doing this until we come back to like the head of a loop or just code that we've already visited. And at that point, again, we fetch the instructions, decode them, and feed them to the rest of the pipeline. So the older architecture very much relied on fetching and decoding instructions, even if you've visited them over and over again. There is a small exception to this, and that's this block here that I've labeled the LSD, stands for the loop stream detector, which is this unit in the architecture that sits there and waits and looks at UOPs, trying to detect a stream of UOPs that resembles a loop. It's kind of a small window. When it sees this loop iterate a whole bunch of times, after a while it says, hey, I have this stream of UOPs that's this real tight loop, so I'm just going to run these as fast as I can, and it shuts off the front end fetch and decode. So we no longer fetch and decode, and we just feed the rest of the pipeline with this stream of UOPs until we hit a brick wall. And that brick wall is typically the last iteration of the loop back edge, which is going to mispredict because we're just running so fast, we're not even predicting anymore. So good power and performance savings, and I'll talk about this a little later on. So in comparison, here's a diagram of the newer generation architectures. Picture looks almost exactly the same as the previous one, except for the addition of this DSB. So same principle, you're grabbing 16 bytes of instructions at a time. The asterisk indicates that for Skylake, it's actually 32 bytes. Feed these into the decoder, get the UOPs. Now, before we feed the UOPs to the rest of the execution pipeline, we store them in this DSB, which is effectively a UOP cache. And then we keep fetching and decoding until at some point we detect that we're about to fetch instructions that we already have the UOPs decoded for. And we do this based on looking up, indexing the DSB with the address of the instructions. If we do, we say, hey, we don't need to fetch these, we don't need to decode these, let's just start executing out of the DSB. We keep doing this until we reach an instruction that we don't have in the DSB, and then we'll go back to fetch from the front end. So that's kind of like the quick Intel front-end architecture 101. So hopefully these will help us understand some of the examples that I'm going to go through now. The fun part begins. I threw together a few examples. These examples and this presentation are a subset of a much larger set of examples and presentation that I have, but given the 35 minutes here, I just picked a few that I thought might be interesting. So let's look at simple aligning on 16-byte fetch lines. Why do we align on 16-byte fetch lines? Well, like I showed in the first old gen illustration, the architecture fetches 16-byte aligned chunks of windows. So here we have a loop running from 0 to 64 with the disassembly on the right. Don't pay too much attention to the contents of it. It's not that important. What's important is this illustration on the bottom, which represents 16-byte chunks of instructions, and the X's represent how the loop is laid out in this 16-byte chunks. So starting at 49E, going all the way to 4D6 or something. So as you can kind of see, this is taking up 1, 2, 3, 4, 5 16-byte chunks of instructions, and we can clearly do better than that. Okay, so if we shift this back just a little bit, we can fit this in 4 16-byte chunks. So a simple alignment change, and this was worth about 20% speed up on an older Nehalem. So just a simple code locality type example. But wait, speaking of performance anomalies, for amusement, I changed the iteration count from 0 to 64 to be to 0 to 65. So just one more iteration. What happened was that the aligned case slowed down by about 9%. And all of a sudden, the misaligned case and the aligned case ran exactly the same. What? So pretty confusing, right? But I can explain this. So if you remember the one block that I was talking about earlier, the loop stream detector, this is where Mr. Loop Stream Detector kicks in and says, hey, you're past my threshold for what I think is a loop stream. And I'm going to shut off the front end, and I'm going to start feeding the rest of the pipeline with just a stream of UOPs. So the aligned and misaligned case now perform equally because alignment doesn't matter anymore, right? We're just feeding UOPs. And the faster case slowed down a little bit because we're right at the threshold, and we're paying the penalty of a mispredict at the final iteration of the loop. So the idea is as we get more iterations in the loop, this will kind of amortize itself and be an overall power and performance savings. Okay, so why not just always align? I mean, you're looking at the previous example, you're like, okay, so you just align the loop and it ran faster. Well, why we do that? It's good, right? Why don't we just do that and call it done? Well, alignment does cost code size. It does cost performance in some cases where you insert no ops on executed paths. And if you have branches in a loop, it can get a bit of a gamble in some cases. So I came up with this example to illustrate this. This is a much bigger loop. I don't have the source of disassembly, not important. But the loop is all the red and yellow is the loop. And the red is the hot path through the loop. Okay, so the yellow is cold. So we got some branches in here. Now, if we blindly align a loop like this on a 16-byte boundary, this has the effect of pulling all of the other lines back in too. So a loop that effectively sat in 4 16-byte chunks now all of a sudden sits in 5 16-byte chunks. And this particular example that I wrote was worth about 80% slowdown on core Nehalem. It actually was a pretty nasty effect. It missed the LSD and had all sorts of other issues. So alignment, not always good in my opinion, and I'll talk about this towards the end of the presentation. Okay, so now let's move on to more current gen architectures, breaking the instruction bottleneck. So fetching 16 bytes of instructions at a time can be pretty limiting. Some of these newer instructions are pretty big with the new ISA. So a simple move UPS here is 9 bytes. You stick a couple of those next to each other and you're already past a 16-byte chunk. You have to pay the power and go through the restrictions of the decoder, and it's just, we can do better. The LSD tries to help by replaying UOPs, but it's very limited in what it can do, and it only looks at loops. So ideally, what we'd like to do is to cache arbitrary UOPs for replay, and here's where the decoder stream buffer, the DSB that I mentioned earlier, comes into play. So what is a decoder stream buffer? It's this cache for UOPs, as we've already mentioned. It extends the front-end window to 32 bytes to increase throughput. And obviously, it saves power and lowers mispredict costs because you've got a shorter pipeline now. What it looks like is it's 32 sets. In each set, there are 8 ways, and each way can contain 6 UOPs. Okay, so that's a nice chunk, about 1,500-ish UOPs that you can fit, which is pretty decent. I think studies are on average 80% of applications execute out of the DSB, and if you're in a hot loop, it's hopefully 100%. So it's kind of a nice deal, but it does come with restrictions, and these are all listed in the optimization manual. So let's go through some of them. So the UOPs in a way must be in a 32-byte aligned window. Haha, this is where alignment comes in. So if you want to put UOPs in a way, they have to be from the same 32-byte window. You can't mix and match. There are only 3 ways are allowed to be assigned to the same 32-byte window. So if you have a 32-byte window that has a ton of UOPs in it, you're only allowed 3 ways. Only 2 conditional branches are permitted per way, and an unconditional branch will always end a way. So if you end up putting an unconditional branch in the first way, UOP of a way, then you've just wasted another 5 UOPs. Entry into and out of the DSP is through a branch. It becomes expensive to enter and exit the DSP frequently, and if you want to hit the LSD, you have to have all your UOPs in the DSP. So kind of like the DSP at a high level. So let's look at some examples that affect the DSP on newer hardware. So similar to aligning on 16-byte boundaries to appease the front-end 16-byte fetch lines, how about aligning on 32 bytes to appease the DSP lines? So the DSP looks at 32 bytes at a time because the ways map to 32-byte chunks of instructions. Here's a simple loop. Again, the content's not too important. The yellow is the hot path through the loop, which is the inner loop. And the 16-byte chunks below represent how this loop sits in the instruction lines, and the yellow circles are 32-byte aligned circles. So the hot path through this loop spans 3 16-byte chunks, and more importantly, 2 32-byte chunks. Okay, so the DSP is going to have to stick these in 2 different ways. Now, if we shift this, not align it, at the head, but if we just shift it down 16 bytes, we end up fitting the hot loop into one 32-byte aligned window, and in this case, giving us about a 30% speed up on newer hardware. So again, kind of a simple example. Now, let's get into more interesting examples. DSP thrashing. So this particular example, some of you might have seen. This was a Bugzilla report from a few years back that someone sent me mail and said, "Hey Zia, there's a unsolved alignment Bugzilla report in LLVM you might want to take a look at." And I was like, "Yay, alignment! I'll take a look." So the issue was that there's this loop that, depending on how you align it, performs massively differently. And I took a look at it, and there are a few cases that kick in with this particular loop. And one of them was a nice classic issue of DSP thrashing. And I'm going to illustrate how DSP thrashing works. So the loop is, so we've got this switch statement with a bunch of cases in it, and it processes a stream of data coming in and switches and does stuff based on it. Not terribly exciting. The disassembly for it is here on the right, and I've listed the DSP restrictions here on the bottom for reference. So the important ones are the first 3 that we're going to concentrate on here. So remember, the UOPs in a way must be in a 32-byte window. Jumps will always end away, and you're only allowed 3 ways per 32-byte window. So we're going to walk through this case, this disassembly, and see how it fits in the DSP. Okay, so the first, from the top, we have 83F0 is where we start. So the first 32-byte window is going to be 83E0 and F83F0. Right, so all of those instructions are going to go in one way, and then we're going to stop because we're going to hit 401, and 401 is in another 32-byte window. So this next instructions are going to have to go in a different way. So we grab these 2 branches, these 2 UOPs will go into another way, but then we stop because rule 2, a jump always ends a way, right? So we got 2 UOPs in this next way. We're still in the same 32-byte window. We grab the next 2 instructions, put them in another way, and we have to end it, right, because of this unconditional branch. Then we grab the next 2 instructions, put those in another way. Again, we're ending in a branch. And if you look at the IPs for what's left, we're still in the same 32-byte window, but rule 3 says we're only allowed 3 ways per 32-byte window. So these will unfortunately have to go into one of those 3 ways, but we've run out of ways, so we end up having to kick out UOPs out of a previous way that we used, stick these in the way, and then the next time we reach the code from the other instructions that we kicked out, those end up fetching from the front end, kicking out something else, going in, and thrashing, right? And, if, as I wrote here too, if going in and out of the DSP frequently is pretty expensive. So if we shift this just a little bit so it sits slightly different, exact same code sequence, but sits differently. Then let's see how else we can fit this in the DSP. So in this case, we can fit all those instructions in one way because they're all 400 and 410. Then we get to 420, and this goes into a different way, and then the last set of instructions also go in a different way. So everyone's happy, right? We got two 32-byte windows, and we don't have any more than 3 ways per 32-byte window. This example, I did some hardware counters on it just to illustrate what's going on. SEP reported DSP to myte switches. Myte is the front-end fetch unit. So the number of switches going from the DSP to the myte went from 312 million to 37 million. And just for fun, I looked at the LSD cycles because now all the UOPs are in the DSP, so the LSD can fire, and it went from 32,000 to 1 billion. So good things are happening, and again, this was worth around 30% speed up. So kind of a fun example. I got a teaser here. So this is the exact same code sequence, slightly different alignment, over 5x slowdown. I didn't have too much time to get into this, but if you want more details, I can talk about it later. Okay, so this is my last example. So I've shown cases where you can align for throughput. I've shown cases where you can align to appease the DSP. And now I'm going to show a case where aligning actually affects branch prediction. So the branch predictor sits early on, very early in the pipeline, and it looks at IPs, not instructions. So alignment does matter. And when it looks at these IPs, it tries to detect where the next IP is going to be to steer where you're going to fetch these 16-byte chunks from. So this example shows a simple function with a bunch of inputs and an if condition that does 3 checks. If any of those checks pass, we fall into some code that does another check. Can you guys see that yellow well? I'm sorry. On the right is the disassembly for this. The red checks, yeah, I'm going to use the laser pointer. The red checks here map to the red checks here in the disassembly, and the yellow check here maps here. Okay, so this particular example is actually mentioned in the optimization manual as avoid putting 2 conditional branch instructions in a loop so that both have the same branch target address and at the same time belong to, that means their last byte belongs to the same 16-byte chunk. So as we can see here, we have a branch that goes to 40050D and another one that goes to the same target. And the last byte in these branches is both in the 550 chunk. So what happens here? Well, obviously some case of aliasing going on here, right? But what? So what happens is the branch target history kind of gets messed up in this case. So architectures have this branch target history that whenever you see a branch, you take a branch, you update this branch target history so that you can predict the following branches that you come up to. It's just kind of like, okay, well, where did I come from last? Then if I came from over there, then that means this time I'm going to go over here. So in this case, we're aliasing issue where these 2 branches kind of alias each other somehow in this branch history information. And if we come in through this if condition on this first condition, this first expression, when we hit this if I equals 0, we still, I mean, by visually inspecting this, we're not sure whether we can predict this properly. But if we hit the second condition and come in this branch, can we predict it? Yes, we can perfectly predict this branch because we know that I was equal to 0. We came this way. So whenever we come through this path, we know that we're always going to take this. So the hardware can perfectly predict this. So I picked an example where we can visually, as humans, be able to predict this too, but it's obviously a lot more complicated in the hardware. And then if we come through this last path, again, we're not sure whether we can take this or not, so the prediction is questionable. But in this case, the hardware can't distinguish between these 2 instructions because they're in the same 16-byte chunk. So when we branch back up and come and hit this yellow if condition, we don't know whether we came from here or here. right? They both kind of merge into the same information in the hardware. So it can't make a very intelligent branch prediction decision. So let's add one no-op. Okay, nothing up my sleeves. One no-op to this, shifting everything down, which causes this last branch's last byte to fall into 560, which is now the next 16-byte chunk. Okay. Now, all of a sudden, let's see if our theory works. The branch mispredict counter goes from 300 million to 150 million. And again, 30% speed up on modern hardware. So, kind of fun stuff, maybe. Anyway, it's it happens. All hardware has, their little hiccups and issues. I mean, it's limited hardware. You have caches, you have aliasing issues. I think the point of this presentation is, I think since these issues come up frequently, it's important to at least understand them so that when you see them, you at least have some clue as to where to start looking. And, if you do find the issue, you'd be like, oh yeah, this is that one thing that guy showed, and that one thing. I just stick a no-op here and I'll get 30% because that's the magic number. So, but the question you're probably asking is, okay, well, this is great. It's good to understand some of these, but how, are there any better ways to detect these issues? Well, unfortunately not. I mean, we've been struggling with this for years in our compiler group, and it just pops up all the time. A funny saying we have is, it's just Perl. So I don't know if you guys have experience with this, but Spec 2000 Perl BMK goes up and down 2 to 6% every change set. And anytime anyone sees any improvement or regression in Perl, we're like, it's just Perl, don't worry about it. But there are a few things you can do. Like I mentioned earlier, understanding the architecture is good and important. Read the optimization manual. Look at presentations like this to kind of get a better understanding. And with this knowledge, if you do see those weird perf swings next time, say, I'm going to try to figure this out. Look at some counters before and after your changes. Measure some of the counters that I listed. I tried to show examples of the sort of things to look for. Branch mispredicts is a big one. Delivery, are we fetching from the byte, from the LSD, from the DSP? Are we switching a lot? And then try to come up with some sort of a theory based on your new acquired knowledge. Add some no-ops and try it again and see if it works. If all else fails, feel free to ask for help. At least I'm happy and willing to help. I find this stuff fun. Some future and current work and some ideas. I brought this up earlier, but do we really need to align everything on 16 bytes? All loop heads and a lot of branch targets. Why 16 bytes? I've shown cases where 32 bytes matters, so why not 32 bytes? Well, I think the architectures are becoming less sensitive to alignment as we're getting further away from the whole fetching from the front end part. I did a couple of quick tests. I ran Spec 2000 actually in 2006 with alignment turned off, and it was worth almost 3%, which is not insignificant to some. And there was no performance differences. So maybe we need to revisit whether we need to always align stuff. And maybe we need to focus more on aligning more sensibly or intelligently and try to pick the places where it matters the most to increase performance. The nice thing about alignment, though, is it does stabilize performance more if that's what you care about. There's less chance that if you mess something up above it, it's going to affect the performance of your aligned section of code. So better heuristics to be able to catch some of these subtle cases, I think, would be more useful. And just a final note saying that actually someone, Omer, on our team is actually looking into some of these. He's made a late pass that runs through and tries to catch all of these cases by inspecting whether we're hitting any of these, some of these things that I talked about and more, and injecting no-ops to split stuff apart. So, expect to see discussions or reviews coming up from that. But that's kind of all I had. Hopefully this was useful to some. And if you have any questions, go ahead.
Got to end up here first.
Maybe this question is very naive. So, isn't it possible for the architecture to do the alignment by itself because it has all the previous history? So, what
is it possible for the architecture to align itself?
Yeah, do the alignment or put the knobs by itself because.
That would be really, really hard. Yeah, I don't think that's a possible thing to do. I mean, it would have to shift everything and readjust everything.
So this is a feature request from Intel. So I can understand how in the compiler it's very hard to always make a good choice to avoid these situations, basically to optimize so that we never hit them. But would it be possible for Intel to contribute a pass which effectively stabilized performance? So the pass could slow down the code, but it would try to guarantee that the code came out was very stable. And then compiler engineers, when they wanted to evaluate whether their change was actually improving the code, like we could just run the test suite with this enabled. And that would kind of be the criteria for your change is better. If your change improves performance with this stabilization pass, then we view your change as good. And
right. Yeah, I mean, that's reasonable. You know, in the past, what we've done is our QA team would run a series of tests, like playing around with the alignment and seeing whether the regression went away or not, and concluding, okay, this is alignment related. But you can stabilize. I mean, I mentioned this earlier. By adding more alignment, you're stabilizing the code, but you're not necessarily getting the best performance. You're potentially leaving performance on the table, but you're stabilizing it. So align functions on 32 bytes, loop heads on 32 bytes, branch targets on 32 bytes, and you're gonna have a very small chance of causing swings because you got all these barriers. But it is potentially gonna cost you performance, obviously, and code size. But I see your point. It's a reasonable thing to do is to have a mode of, okay, I want to test this in a stable environment to see it before and after.
Right. In particular, a mode that Intel owned and could say like, okay, this is what we think the right recommendations are of how to stabilize.
Right.
And instead of having to like look at a presentation, it would actually just be in the code base.
Sure. So someone mentioned that there's already an option that does this?
There's already an option you can use that causes the code placement to line pretty much every block at a granularity of your choice. That's a great way to stabilize for testing, though it is not, as he's pointing out, it is somewhat terrible for performance depending on your workload.
I'd like to move on to the next question.
So this may be a bit of an obvious optimization you could try, but would you recommend, for example, on switch statements, you've got small blocks and very large blocks, trying to mix the small blocks within the large blocks to avoid, for example, the DSP thrashing?
Mix the small blocks and the large blocks.
Did you guarantee that you don't have a lot of small blocks in the same 32-byte window?
Right. Yeah. I mean, there's various strategies you could use, and mixing those might work in some cases, or, you know, simply just moving the blocks completely out of line might work. Because a lot of the times with switch statements, you go to a case and then you jump back somewhere anyway. So you got this unconditional branch. So you could move your switch just in, you know, far away places and just pay the cost of the jump back up, which you're going to have to do anyway. But yeah, there are a few things that you could do to solve that. Yeah.
In your presentation early on, you were showing Atom and Core, and then you switched to Ivy Bridge, et cetera. What would these optimizations have been if you showed examples for both architectures? Meaning usually you compile and target the oldest thing you think anyone's going to run your code on, not necessarily the newest.
Right. So obviously if you're run the example that I showed that affected DSP thrashing on an old Nehalem, it's not, well, it might have some effects, but they're not going to be the same as the ones that we described. but on the older architectures, perhaps it makes it easier to analyze because there's fewer variables that you have to worry about.
I guess so if you did all this stuff for the new architecture and then ran on the older architecture, would you?
I see. You're saying that if you tune for a new architecture, is it gonna cost anything for running them on older architectures? Well, whenever you start adding no ops, even if it's to avoid performance, there's always the risk of costing, well, at least code size and potentially performance. You could be, anytime you add no ops, you run the risk of shifting something lower down somewhere that's going to make someone unhappy, which is kind of why I showed the example of aligning loops that have a lot of branches in them. Alignment seems to be a good idea and make sense, but once you got all those branches, then it's a hard problem to solve, to make everything happy and everything align well, especially when you do these, it shifts everything below your code. So I don't know, that didn't exactly answer your question, but.
Have you considered some middle-end strategies or heuristics to consider jump threading, loop inversion, or if conversion strategies to mitigate these issues?
It hasn't been considered, but as all optimization manuals say, and as a general guideline, the fewer branches you have, the better. Every time you reduce a branch, you're going to, it's a good chance you're going to improve performance. So doing jump threading and if conversion and things and potentially reducing branches will help, but it's unclear how much it will help for alignment purposes. You're going to help, well, obviously execution of instructions and especially branch prediction is going to be helped a lot. But it's unclear. We haven't really explored the effects it has on alignment and avoiding these cases.
It seems that it will have ESV thrashing, the last example, for
Sure. And also the example with the branch predictions, because the two if conditions were the same, right? You could thread that condition and avoid the thing. But yeah, good ideas.
Early on, you mentioned that this is part of like a larger thing, but you had to cut it down to 35 minutes. Is there like another slide deck somewhere that has the other examples?
Yeah. I want it all. Yeah, I do have some, and I can share those with you. And I have a whole bucket of lots of examples. So I'd be happy to, if you're interested, just see me after and we can trade names or whatever. Yeah.
We have time for one more question.
Are the hardware guys insane?
Well, like I said, it's not. Hardware is limited, right? You have limited cache, you have limited indexing into these caches, and there's always going to be some sort of alignment or aliasing type issue. So I don't know. I haven't compared this architecture to other architectures. So I don't know whether other architectures are completely free of these sorts of problems. I doubt it, but maybe less. But we have been working actually with the architects to help reduce some of the more severe cases, at the very least, to have them not necessarily look at static traces to be able to base performance on the next hardware, but to look at similar traces that have shifted IPs, because you're never going to find these cases if you're just looking at one trace with one set of addresses burned into it from architecture to architecture. You really need to look at two different ones and see the deltas. So we have approached them, and they have agreed to looking more into that. Okay, sorry.
So just looking at a lot of these examples, it seems very counterintuitive, at least at first glance, what you would have to do to mitigate these alignment issues. And I know that a lot of people have demonstrated success in the past by using techniques like stochastic optimization, where you just do a random search, you see how it performs, and you iterate. And the question is, if we would like to apply stronger formal methods, like SAT solving, for example, is there somewhere a formal model that would tell us exactly? I mean, you have these rules that say, thou shalt not include more than 3, etc. But is there a fully formal spec that would enable us to do richer analyses based on formal methods?
Well, there's what's in the optimization guide, obviously, but there's more. I mean, I have examples too that I can't share because they would need me to have to share actual algorithms that are secret. So no, we can't share everything. We can share what's in the optimization manual. I mean, I guess those go all through the architects, and they decide what's okay and what's not okay to share. Beyond that, I don't know. I mean, another problem with this whole issue is that you figure out all these gotchas, and then next year a new architecture comes out, and you have new ones, right? So, I think the best you can do is just use that -m tune function to say, okay, if this is this, then do things slightly differently, and investing a lot of engineering resources to do something that complex. I don't know how much the payoff would be, but it's a reasonable idea to kick around and think about.
Okay, thank you very much, Zia.
Oh, thank you. All right, thanks, guys.